All right, for this homework assignment, I decided to do 43, 53, 81, and 89, which covers some of the basics in terms of going from a sequence to the general sequence and expression, or in the notation, and then looking at summation notation in both directions, going from the actual summation notation or going from a summation statement to the actual summation notation. So first off, when I look at 43 and I want to write a general expression of a sub n, I look at, well, I have a fraction and I look for what is varying. So in the numerator, I see that the numerator is going up by 1, and so I want to start off with an n here, but we know that if we start off with n being 1, we want n being 2. So if I want the first number to be 2, and I start off with 1 for n, as we always do, if I put n plus 1, if I plug in 1 for n, I get out 2. And then it's increasing by 1, because it's just 1n. If you think of it in terms of like a linear equation, you have a slope of 1. That takes care of the numerator. In the denominator, we're going up by 2, and we're starting with 1. So if I tried 2n minus 1, since it's going up by 2, I have 2n. If I just do 2n, those are even numbers. 2 times 1, 2 times 2, 2 times 3. If I do 2n minus 1, those would be odd numbers, because if I plug in 1 for n, 2 times 1 is 2, minus 1 is 1. If I plug in 2 for n, that'd be 2 times 2 is 4, minus 1 is 3, and so on. So that will be our arithmetic sequence for this particular sequence. So for number 53, this is a recursive statement where a term is based on its previous term. So what that means is, since this term, a sub k plus 1, sorry, it's a little sloppy, I don't have my stylus with me, so I'm just using my finger. It's not as nice and neat, so my apologies on that. So a sub k plus 1, we see that this term is based on the term before it, because the term before k plus 1 is this minus 1, just like the term before 5 is 5 minus 1, or 4. So if I want to determine, I already know what a sub 1 is. It says find the first 5 terms. Well, the first term is a sub 1. The next term would be a sub 2, which would be 2 times, if I plug in, so if you note here, 2 is equal to all of k plus 1, so then k would equal 1. So this would be a sub 1 minus 1. And they already gave us what a sub 1 is. It's 3, and that's from above. So if a sub 1 equals 3, I'm going to plug that in, and now I'm going to simplify. So 3 minus 1 is 2, 2 times 2 is 4. A sub 3 is going to be 2 times a sub 2 minus 1. And now we have 2. A sub 2, we just had it right here. A sub 2 equals 4. So we plug in a 4 there. And now we have 4 minus 1 is 3. 3 times 2 is 6. I keep in mind that your index is like your input of the function, and then your a sub n, or this time an a sub 2, is like your output. So when I know a sub 2 equals 4, I see a sub 2 here. That's kind of like saying f of x or f of 2. F of 2 or a sub 2 equals 4, so I plug all of 4 in for there, and then you get 6. For 81, they give us the summation notation, and they say find the sum. So what we're going to do is, what this notation means is we start out at k equaling 2, and we plug in k being 2, and then we plug in 3 all the way up till we get to 5. So the first time, I'm going to put an equal sign here, just like this is an equal sign up here, just coming down here. So the first time we're plugging 2 in for k, so I have 2 plus 1 squared, I plug 2 in, minus 3. That's the whole summation for when k equals 2. Remember, what that notation means is we're going to add it to now 3 being plugged in for k. So 3 plus 1 squared, 3 minus 3, plus, I'm running out of room, so I'm going to come down here. Now I'm going to plug in 4, so I have 4 plus 1 squared, 4 minus 3, and this top number again is the last value or the last input you are going to substitute in for k. So last one I plug in 5 plus 1 squared, and then 5 minus 3, and then we just go ahead and calculate. First one right here, 3 squared is 9, minus 1 is negative 9, plus, I'm going to look at the next one. I have 3 plus 1 squared, that's 16. 3 minus 3 is 0. 16 times 0 is obviously 0. Plus, next one I'm going to simplify. 4 plus 1 is 5. 5 squared is 25. 25 times 1 is 25. And then the last one, 5 plus 1 squared is 6 squared is 36. 36 times 5 minus 3 is 2, so 36 times 2 is 72. So if I combine all of those, I get 86. Do that right? Let's see, 989 minus 797 minus, or 88. So for 89, we're creating the summation notation for this particular series. Remember, sequence means sequence of terms. Series means the addition of that sequence, and here we're adding the terms, so it's defined as a series. So at the bottom, I am going to write what our index is. It doesn't say in the directions what you have to use. I am going to decide to use k. And what I want to do is look within these expressions for where a number is varying. Well, if I look at the numerators, they're all 1. And note when you have this plus, dot, 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 plus, it just means that whatever pattern we have here, it's going to continue on in that pattern until we get to here. It's just a fancy way of, or the efficient way of not having to write 1 over 3 times 4, 1 over 3 times 5, and so on. So I see that this 1/3, 1/3, 1/3 is constant throughout each of the terms, so I'm just going to write it like that. And I see that it's starting out with 1 right here, so I'm going to start out the 1 here. Sometimes you may start with a 0, you may start with a 2, but typically we like to start with a 1 or a 0. 1's the preferred. And there's multiple answers for this, but if we start out at 1, which is the same number as that one, this makes this really nice and neat, and that's just going to be k. And then we want to look at the last one because that's going to indicate what we want to put on top of the sigma. And the last one is 9, so there is our sigma notation for 89.